So, allow me to continue from where I left off last time. If you remember, we went out into the workshop and we were trying to fabricate this piece. This piece was, we see a little carefully, bottom part of a antenna assembly. So, I have here, this is the one that day in our fabrication shop, my colleague tried to fabricate it and show you. This is the real piece. Part of it in the real piece, what you see is, you see here on the corners here, is a small this thing, this is the one we saw here, and then this small step here is intended because of the sheet metal, that machine what we have there. We have a folding machine which has clamping fingers, and then the bottom jaw part of it, there is a limitation about the depth with which we can go. Hence, this cutout was necessitated when we tried it last time. So, eventually the piece looked a little like this, but you see it is not as clean and as flush and natural as it looks. However, in real life, it is expected when these things are delivered to you, and then especially if you are a consumer or not an industrial consumer, all these small imperfections have to be accounted for when you make the design. And now if you go to the top portion of this, see here, it did not come out well. For some reason, somebody could not properly account for all the small imperfections which are likely to take place in the case of the fabrication there. Have you seen it? Little issue with it. This is the reason why we expect engineers to start their work to be familiar with the fabrication process. This whole thing was cut out on a 90-degree notching tool, and then when we attempted to bend it, it turns out that it is not a 90-degree bend. There were some other issues with it, hence we ended up with what looked like obvious flaws in the design. These are not necessarily flaws in the design, it is just that they all have been adjusted by the constraints in production, which are specific to the machine, specific to the various conditions of bending and so on. So, you have further drawings here. I think I showed you this drawing already. Seen here right from the front, we have a small flange here, there is a motor, and then it is part of some antenna or something which needs to be rotated and so on. I will stop here. Now, I will take you to a very familiar electronic object you are likely to see. This one is called a EI lamination, because obviously because of the shape. Typically, the proportions have been so adjusted that if this is an E and then grains are in this direction, see, no, they are flowing in our drawing, no, left to right or from this. And imagine this small thing, what you call this eye portion of it can be cut out of this portion, then these also will be in the same line. So, if you are to make a transformer, a majority of the lines or the what you call magnetic lines of force will follow the grains, and miraculously the total material wastage is small. So, generally it is expected that this total height you have here A, and then if you take this C, if somehow you make A twice as much as C, and then you have two E's facing each other in one stamping, which is 2 times B and 1 times A, and then it is a strip A times wide and then B times and a long strip. It is possible for us to have a zero waste lamination. So, 2 times B will have 2 E's And then this, I have told you, if you can somehow make C has half of A, you will end up with a beautiful I portion of it also. This is how typically optimization is done in the tools which are used for this. In this case, it is probably made with a die, a stamping die. So, you have a progressive blanking and die where the strip is moved continuously and then all the time the operations take place, and in the end you have a beautiful stack of nice, see, laminations like this. I have a beautiful stack now, if you see here. And then maybe if you observe carefully, the proportions have been so adjusted that this E and I can probably be made from here, or the I punched out here can be used in the next lower size of the lamination. This lecture is not about how to optimize EI laminations, more about how to make our own sheet metal work after you are aware of various operations and this. Now, I would like to get back to one of my small box like things which I started with. If you remember, this is the picture I was trying to show you all the time. Can you see it now? You can see there is a bottom chassis part of it, then the top cover of it. So, all the dimensions are known, and then in one of the earlier drawings I have also showed you how to make sure that the top and bottom fits. However, this one, the picture you see has a zero thickness, they are all planes in space. Now, in reality you cannot really have an object which has zero spacing, zero thickness, and between the top cover and this, if you take the outside dimensions of these two limbs, and then they have to coincide with the inside dimensions of this. So, whatever thickness you have, you still have a small portion. Similarly, if you go up now little close, up close to this portion here in the corner, very conveniently they are just sitting together occupying the same space, two edges. We have an edge here, and then left side also you have an edge here. So, when these things occupy like this, you end up with a real problem. Now, imagine, for clarification, I have turned it over so that you can see how the bending take place and all, but a real life object now is likely to be thick. There is a thickness associated with it. Now, you see the moment that thickness comes, a few of the assumptions we have made may not be very valid. See here, see this corner. Similarly, if you go down, you see this corner also, but this corner is a little more visible. So, I will take you to this corner. Two or three small things have happened. One of them is it possible to fabricate a piece like this where the internal dimension from here to here should be exactly equivalent to the limb dimension here. Two issues are there. One is, if we take that this cover is overlapping on the other, I think the next picture shows you those things. So, if it is overlapping like this, you need to very carefully calculate various dimensions here. Now, already I have made a small jump here. Have you noticed? While this one is a sheet metal enclosure with only a thickness, but in real life when you want to carry out the bending, as we have seen in the demonstration downstairs, have you seen here a radius is there that involves two radiuses. One is an internal radius of the tool when we try to do the bending on the bending press or the brake, and then the sheet thickness itself. So, typically depending on the constraints and depending on the behavior of the material, at least 0.5 millimeter internal radius is preferred. Unless the sheets are very thin, in that case it can be proportionately smaller. Typically a rule can be, what you call rule of thumb can be, at least it should be 1/4 of the thickness of the material. So going by that, if this is a 1.6 mm material, this can be around 0.6, I am sorry 0.4 millimeters, and then after that you have a outside bending. Now we will come back to this corner of this. Have you seen here again there is a bending here which may or may not be required. However, this bend corresponds to this bend here of this top cover. Why this is required? Because after you finish, it should fit neatly one over the other. If you have a clarity of your concept, now you see they appear to fit quite close. So you have in this corner, I have an internal bending radius which is dependent on a little on the machinery we have and the tools we have, plus something which is related to the external bending, the thickness of the whole thing. Now together, if you now place them, they seem to fit nicely, absolutely no issue about it at all. I have a beautiful box here. See that it seems it fits. And now coming back to the old demonstration again, it looks nice, but then anything you have, any front panel you have here, all these things must be done before the operation, that is in the flat condition. So generally what is done here is we try to find out the actual panels of what fits where inside. This is where all the thickness compensation and all will be there, and then eventually try to lay them out flat. You see there is a small gap here, can you see here? In the corner there is a small gap, this is not meeting here, this is not meeting here. So here now first time we end up with trying to work around or make proper blank or sheet metal calculations. Why this is important is, you will notice that any errors or anything, any decisions taken at the top are likely to affect the bottom. So if you are little familiar with it, chances of their failing will be small. Something again very much related to this is, if you interact directly with your fabricator, he will explain these things for you. And then you will notice is probably you want to have some mounting holes, you can have a standoff, and then you require some holes for taking various nuts and bolts and all that. So as we go out, we finally have a tolerable, neatly done enclosure. But here again you notice here, we talked about a spring back. So when you want that spring back, this U needs to bend in a little so that it can come out, and in this corner you need a small gap here to ensure that the bending takes place without any problem. Understood, no? So in the corner a small notch is required. Usually these are all details which are to be done by the fabricator, but then it is still useful for you if you can follow these things. While it looks so good in a 3D rendered drawing, reality is this. Reality is, you see here what the thickness is started, and then it does not close as well as you want, especially if the materials are little thicker than what we are looking for. So at this point I would like to draw your attention to what is called bending elements and overview. I have 3 files here, and one of these files, the person who has uploaded, he has given a open license saying you are welcome to use it, but then in the original condition. So at the end of it, it comes here, and this is old, it is nothing new. And then very important thing is, it has to be tried out, and it is very specific to the conditions of the raw material, conditions of your operation, and then conditions of the machinery they are using. And again related to all this is what are the type of errors that can happen and so on. So, we will start with all those words which we are talking about. It is a term which describe how much material is needed between two panels to accommodate a given bend. And notice here, while being oftentimes tricky to determine and easy to predict and calculate for many standard circumstances, determining bend allowance is commonly referred to as bend development or just simply developed sheet. So, some of you have played with origami, and typically if you have made a pinwheel, take a square, cut through the halfway through the diagonals, bend over, and you have a pinwheel ready. You will notice that it is a wonder. It's I mean it keeps you occupied, and you will know what we are talking about when we talk about a bending allowance. So, in this case we see carefully there are two ways of determining that. One is take the external dimension. This is what I was talking to you about there. If it is a simple L shape, external dimensions are easy to measure, and if it is a U also we can make. But if it is a Z section, you need to find out what constitutes the external and what constitutes the internal. This is the bend radius I was talking about. The allowance is what we give extra there. Now, we need to calculate this flat length. If you can recollect what I had shown you at that time, when we tried to make something which is 240 mm and total of 185, we ended up with a little extra length than the nominal lengths we have taken. Most important, no? Read this. It does not bend allowance are calculated for a part and used to make costly tooling or production part that require a lot of labor to produce. A scrap tool or production run can be very costly, much more so than a test piece. So, if you are ever not sure of your development length, make a test piece to confirm your development. That is what we have done there. In that case, I have asked my colleague to make a small strip which is 20 mm wide by the total thing. One of the easiest ways to make a test piece is shear a piece of an exact length and form it using the process that will be used. After the part is formed, the part is measured and compared to the expected lengths. The bend allowance is adjusted as needed. You see this, no? Critical thing is adjustment. It is the physical process which leads to the equation and not the other way. And the equations in the given set of conditions ensure reproducibility and not the other way. This cannot be taken to some other material, cannot be taken to some other way of doing, including rate phenomena. If you use impact, they behave slightly different from if you use a gradual operation. When hard tools are produced, laser cut blanks are used to validate the forming tools and part development before the cutting tools are completed. And this is what I was telling you. This is taken from this called sheetmetaldesign.com. Towards the end on the page 12, the legalese or release is printed there. Generally the release is, yes, it is released for a purpose of learning, but then not binding on us, or it is not a mathematical exposition in which you try to prove all the conditions and so on. So, read along with me. While most bend developments can be predicted with ease and will develop correctly, there is no perfectly scientific method for predicting bend allowance due to the many factors: actual versus planned thickness, forming method, and the given part tolerance. Many companies will develop their bend allowances based on formulas, forming practices, historical, what trial and error is given there. Again, two words, scientific and trial and error. Is it an oxymoron? Not necessarily. Science is not predictive as we think it is. It is a little analytical. and then that analytical component if we use again, we can come back to reproducibility. So, in our traditional method, the idea is anything which you give here is predictable. That last page Legalese was talking about, they talk about do not take it as a rule, in case there is any mistakes do not sue us. So, let me move on to the difference between a lazy bend and a bad development. You have seen that, no? I think I will leave you to read the first para yourself, my voice I will avoid. Sir, let them read it, put me the other thing. It takes some time to validate tooling and make sure everything is tuned properly. Not uncommon, but apart with the correct development will have features that act long because of lazy forming. The most common cause is not bottoming the forming tools adequately. Eventually, they will tell you about what is bottoming, what is coining, what is air bending, 3 things. Most important again in this, no, if you read along with me, first general principle, you have seen that neutral axis that part of the length which does not change is the neutral axis. You would have seen it when you bend anything in your hand, typically a small flexible material and play dough. When you bend it, you will notice that inside gets compressed and the outside gets stretched. And you see the neutral axis is not exactly in the center. You have seen that, no? It is not a geometrical center. A part that is bent over a sharp radius when compared to thickness will stretch more on the outside, which means neutral axis will lie closer to the inside of the bend. The issue is about the location of the neutral axis. Based on the material thickness from radius, form radius and method, the ratio of compression to tension in the part will change. So, it is not a simple this thing, and then it is also a rate phenomena. If it done gradually as in a hydraulic bending thing, bending machine, and time is given for it to accommodate the various things, bend will have less outside stretch, neutral axis closer to the center of the part, that is nearer the geometrical center. Now, if I go up, same thing, there is a material in tension part which I was talking to you about, which is here, and then there is a material in compression. You see here, tension versus compression, it also relates a lot to the direction of grains and the physical structure of the material. So, some materials have a tendency to open up here, means there are, while it is not a crack actually, there are more gaps here than natural, and here all the gaps, there is a physical limit. After a small time, everything is in compression. As such, not much of compression can take place and tension can be more. So, if you go up, tension ratio depends mostly on geometry. When there is a smooth radius, so in plumbing we call it a long elbow. If you see a pipe and then if it goes like this looks a little like the long elbow, and this looks like a short this thing, and then we really do not have square bending like this, no, we really do not have something is absolutely square, though I mean we would like to call that something is absolutely square and there is nothing. Such a thing does not occur in normal sheet metal. Going back to my this picture from sheetmetal.com, you have seen here, if it is a tight bend radius, the neutral axis seems to be about 1/3, and then if it is a large bend radius or a gradual bend radius, it exactly forms the geometric middle. Effectively, we have this issue where the neutral axis situation in a bend is commonly called the K factor. It is signified K in the development formulas. Since the inside compression cannot exceed the outside tension, K factor can never exceed 0.5 in use. The neutral axis cannot migrate past the midpoint of the material. A reasonable assumption, the K factor cannot be less than 0.25. Mind you, it is again a assumption. Then I was explained earlier, no, I mean I cannot give you an answer, okay, it is alright, what is then the K factor? Subsequent lectures will explain to you about the things here. The neutral axis migrates based on the compression to tension relationship of the given bend. We have this, no. So, we have, you see here, even the cross section does not seem to be constant, it thins out. So, if you take deep drawn parts like a can and all that, sometimes you would have noticed as if the pieces are torn and the thickness is not the same. Inner and outer radii are not necessarily concentric. Material in compression bunges inside, outward push. So, we see here a completely bent over 180 degree bend. So, can we actually make it flat? Some conditions, yes, depending on the softness of the material. The reality is that usually, though it is not easily visible, a small gap will be left there. In this case, no, it is given approximately 1/4 of the thickness, a little over 1/4 of thickness. When I showed you the small cover for the power supply unit, it is a small cover and it is very thin. To make the edges stiff, they have bent them over, formed something like a little like a bead. Technically that is not the name, but however the whole thing, no, what is here, it completely made like this flat. You have a nice smooth edge. Important thing, no, is that smoothness, otherwise it will become like a shaving blade, very, very sharp. And then because of the shearing operations, the shearing operations are there, one part of it will give you a really harsh edge. So, if you fold it over, first thing we managed is we have got a very smooth radius and slight improvement in the rigidity of the material. So, if you can now just make something, no, like this, a small thing, you can increase the stiffness of the material as well as make the bending easier, but then all the thicknesses have a tendency to accumulate in your part.